Hello. Imagine that we encounter a system of differential equations that looks like this. So there are some restrictions, namely we have n unknown functions, y1 through yn, and for each of them we want to get a formula for its derivative, which is very useful, but also practical. In applications, differential equations very often come exactly in this way, so it's not too restrictive. And notice that we do not really care what's happening on the right. There are some expressions that feature the unknown functions and also the independent variable. We call it t, not x, and this will come handy later on. The obvious interpretation is that t is time. It need not to be so, but it's convenient to imagine that it is time. And in particular, if this comes from applications, then most likely this system is not linear, and perhaps it's even unsolvable analytically. And yet, we want to use this system, these differential equations, to gain some understanding of how the process which it describes actually works, because such a system may describe, let's say, some mechanical device, or some structure, or perhaps some process which is happening around us. So we want to see in what possible ways it can develop in time. We want to see what to expect from it. And we asked a question like that before when we had just one differential equation. And we got a big help from a visual representation of solutions. We tried to plot many solutions of different kind into one picture. And then when you look at such a picture, you get a visual feeling for what's really happening in this system. And that's exactly the topic for today's lecture. And let's start with this example. It's a simple 2x2 system, but it's definitely not linear. In the first equation, the unknown function is being squared, and this essentially buries linearity for the system. But even if the first equation were linear, the second equation would spoil it anyway, because here we divide those unknown functions. So this is definitely not a linear system, but it's special. By an extraordinary piece of luck, I know the solutions. For instance, y1t is e2 negative 2t, y2t is e2 negative t. Now you can check that this is actually a solution. You just substitute it into the formula, you will get it. This is a realistic example, at least we pretend so. So I will use realistic range of validity, t greater than or equal to 0. So that's one solution. And don't ask me how I got it. But the question is, how can I visualize it? Or in general, when I have a system, I get a solution, but now solution means many functions and functions. How do I visualize it? Well, the easiest thing you can do is just plot the graphs, preferably in one picture, so that you can see how they interact, those functions, because they belong together. It's a pair of functions, which is one solution. So let's have a look at it. Here we have a little code. And when I run it, I can see two graphs. The one which is darker, if you can see that, the one which goes steeper down, which we can see over here, e to negative 2x, this function goes to 0 faster than this function. And that's exactly reflected in the graph. The one which is hugging the t-axis more, that's the function y1. And function y2, that's the one which goes in a slower fashion to 0. But they both go to 0. So when I look at a picture like that, I can see quite a lot of things, if I get lucky. So this is definitely a good way to visualize solutions. And if I had a 3x3 system, 4x4, I would have more curves, and I could perhaps see something really useful from it. However, this is not really viable if you want to get overall picture of the behavior, because then you have many solutions, and each solution is a bunch of functions. So when you plot it into a graph, you may get something like this. In this plot, you can see 5 solutions, which means 10 graphs of functions. Now, I used colors to actually encode them so that we can see which functions belong together. So, for instance, we can see, well, really close to the t-axis, we can see the 2 blue curves. That's the previous solution. But I had to scale it so that we can also fit the larger solutions. So, for instance, in the upper half, there are 2 green curves. One is darker, the one which goes down, and one is lighter, the one which goes up, which turns around. And that's another solution. The darker one is y1, the lighter one is y2. So the darker one goes down. Then there is, let's say, in the upper half, we can see a curve which starts at 10, and lower half another curve which starts at -10. They again belong together. The upper one seems to be a little bit darker. Okay, I go with it. It goes to 0, and the later one also goes to 0. That's another nice solution. And we can keep going like that. Notice an interesting solution, which is the one which is in the pink, and it's on the top and also in the lower half. So the function y1 is actually positive, the function y2 is negative, and they go to 0 and they touch the time axis and they disappear. They do not continue anymore. This can happen actually in this system, that the solution disappears. So all kinds of things we can see in this picture, but now just imagine that I add, let's say, 5, 10 more solutions. This is not really manageable. So we need another way to look at solutions. And there is actually a way to simplify the picture, in a way. When we worked with a system like that for linear equations, we actually gained, let's say, help from linear algebra by imagining that we are working with just one function, but it's a vector function. So that's something which hides complications from us. Let's see. In general, the system looks like this. I have a vector of functions, and when I differentiate, I get a vector of functions. These guys, they form a vector with unknown t and y as a vector. So that's the matrix form or a vector form. Rather, there is no matrix now. So vector form of this system. And by the way, if I erase those vector signs, those little arrows, this is exactly a general explicit first-order differential equation that we covered before at the start of this course. So there is a definite similarity. And now when I look at a solution, I see a vector function. And a vector function has just one graph. Let's go back to our previous example, the one with blue curves, two blue curves, and let's see how it looks like if I interpret it as a vector function. Here we go. This is the graph. So the horizontal axis, that's t, the independent variable. The axis which goes down and to the left, so it's going against us. It reaches into the classroom. That's y1, and y2 goes upwards. And let's see, how does it look like? That's the curve. You can sort of see how it goes through space. Where does it start? That's a good question. When time is 0, we are starting at position 1, 1. Does it work? Well, let me turn it around like that. And I think that the starting point of this curve really does have coordinates 1 and 1. So this seems to fit. We can also see nicely that as the time goes to infinity, our curve is approaching the origin. So that's also nice. We can see all kinds of things. By the way, if I turn this graph in such a way that y1 as an axis disappears, it goes directly against us, then we can actually see the graph of y2, which is the exponential. And if I turn it so that the axis y2 disappears, then we should see the graph of y1, which is an exponential that goes to the origin faster. And I think it does. So it all makes sense. We actually can recover this individual information from a picture like that, but we do see the whole 3D graph. Now, that's a nice way to visualize. It has several disadvantages, and I will get to them soon, and one of them is obvious. If I didn't have a computer on me, I simply couldn't get anything like that. But this is not all that, let's say, crucial. There will be some more significant disadvantages later on. So now we can visualize solutions. There are curves going through 3D space when you have a two-dimensional system, 2x2 system. For a 3x3 system, the graph of a solution will be 4-dimensional, which is where it gets interesting. So let's not worry about it yet, okay? Let's stick to 2x2 systems. We can see the graphs. If I imagine the time axis going to the right along the board, then I can see a whole lot of curves going like that in space in some way. I don't know how at this moment, but anyway, we have this nice idea, this visualization, and we talked about a very special kind of a solution when we were doing this analysis of behavior. Some solutions are really interesting. These are the stationary solutions. What does it mean, stationary solution? Again, that's a grand name for something very simple. It's a constant solution. So you have a function which is actually always the same. always the same value, some vector y0, which is a vector from R to n, in our case, vector from R squared. How does such a solution look like? Well, let's see. Here is the y1, y2 plane, and in this y1, y2 plane, there will be this vector y0, let's say over here. So this is vector y0. And now we attach the time axis, and as the time goes, the solution does not change at all. So it is a steel rod which is running parallel to the t-axis. That's how I visualize stationary solutions. You have a system, let's say some mechanical device, and you can set it up in different ways. And that's exactly what's happening at time 0. You set it up in different ways, and then you let it run, and you see how the situation develops. And if you set up the system in this very special way, which is called y0, then the system likes it and stays that way. So this value y0 is called equilibrium. And again, this is similar to what we did before, for just one equation. Okay, now let's ask a good question. How can I recognize a stationary solution? Well, it's constant, and because it's constant, the derivative must be 0. So we are looking for some value, y0, but now it's a vector value. That's our question. Can I find some vector, which means values y1 through yn, by the way? So I'm looking at it in two different ways, as a vector problem or as a problem with individual functions. Either way, I'm looking for certain specific n values so that if I put them into my equation, they will give a 0 derivative. So I want f t y0 to be 0, or if you want, I want fi t y01 y0n to be 0. So again, it depends whether I look at individual equations or whether I look at a vector, and I simply want this to be 0, regardless of time. That's important. Now, if my system is autonomous, which is exactly what I expect to have in applications, like this system, there is no independent variable in it, then I get a very simple set of equations. I can solve it for y1 through yn if I get lucky, and I get my stationary solutions. So this is exactly the same way we were doing it before, just we didn't have this arrow symbol over here. We just said fty is 0, that's how we were looking for stationary solutions. Now it is exactly the same game. So let's have a look here. Do I have any stationary solutions? That's a good question. Well. I look at it and I say, well, the first derivative of y1 and the first derivative of y2 should be 0 for any constant solution. So this right-hand side should be 0, and this right-hand side should be 0. Minus 2 y2 squared is 0, and minus y1 over y2 should be 0. Now, from the first equation, it's quite obvious that y2 must be 0. From the second equation, equally obvious, y1 must be 0. So this is our candidate for a stationary solution, but it does not work, because when we look at our system, we can see immediately that y2 is not allowed to be 0. That's an important observation. Perhaps we should have started with it, because it's a key observation. It's a key limitation of what we can do with solutions. Okay, y2 is not allowed to be 0, which cancels our only candidate for stationary solution. So there is no stationary solution for our example, unfortunately. So we cannot try our tricks on it, which means that we will need another example. Let's have a look at it. Here we go. How did it go? I know. y1 derivative is y2 squared minus 1, and y2 derivative is y2 minus y1. Okay? Now, when I look at the system, I notice that the second equation is linear. The first equation is not. So this is an interesting thing which is happening a lot in differential equations, that you look at two equations or two systems and you compare them visually and you feel that this one looks more friendly because the second equation is linear, which is good. The first equation is actually quite analogous. So you would expect that this system is actually better behaved. But that's not true, because I can find solutions, analytic solutions for this system, but I cannot find them for this one. This one is unsolvable. So it's in fact much harder from theoretical point of view and also from practical point of view. But it's another story. Let's talk about stationary solutions. Well, I want a solution which is constant, so I want the derivative to be 0. So I want y2 squared minus 1 to be 0, and y2 minus y1 to be 0. So this is actually two requirements. y2 squared must be 1, and y1 must be y2. And from the first equation, there are two solutions. And once I get a solution for y2, I immediately get a solution for y1. So there are two stationary solutions. y2 can be 1, and then y1 is automatically also 1 due to the second condition. So this is one stationary solution. But also y2 can be -1, and then y1 is also -1. So these are my stationary solutions. Now, when I ask about setting up my system so that it works like that, I will talk about equilibria. And there is two of them, 1, 1, and -1, -1. So that's the settings for my system. And here I can see them as functions, as they develop in time, as solutions. Let's have a look at little visualization. Here we go. So I read my system, I hope it's the right one, y squared minus 1, that fits. I relabeled the unknowns. We will get to it soon, don't worry about it. And here is the picture. Okay, what do I see? I see two straight lines parallel with the time axis, which is exactly the picture that I've been talking about. One of them is located at 1, 1, we can see it over here, and the other at -1, -1. So that's the two stationary solutions for my system. Very nice. Okay, so finding stationary solutions is usually not such a big problem. And when we go back to, I think, fourth lecture or whatever, when we talk about analyzing solutions for just one ordinary differential equation, we found stationary solutions. And then we asked a good question. Is this stationary solution stable? And that's something which is very important in applications and for the systems as well. So when you find stationary solutions, that's a very important information, but stability, that's perhaps even more important. How do I recognize stable solutions? Well, let's take this idea that we had for one equation and move it to this situation when we are actually talking about the vector solutions. Here, my system behaves in a specific way that it likes. It's just sitting there, not moving. Okay? But now I reach in and I change the setting of the system a little bit. What's going to happen? Let's say that I do it here at this time. For a stable stationary solution, I expect that this little interference, because I interfere with the system, I no longer at that moment was governed by those differential equations. So let's say that I added some extra term, just for a second, some outside force. But then my influence stops, I stopped interfering, and the differential equations, they again come into the play. And they govern the development of the system or of the process. And I'm asking, will I get back to my stationary solution? That's the key question for stability. And if I do, I'm happy. So I'm, let's say, displacing the situation or changing the situation, and I hope that as I am changing it, I will always get back in the limit to my stationary solution. This is something that I want to see in applications usually. And this is exactly what I need to describe in my formal mathematical definition, but I have to be careful. There are two things I have to worry about. First of all, I cannot really hope that this will work for any displacement. This is a 3D situation, so imagine that I have a rod which is fixed. It's protruding in space, steel rod. I hold it firmly on one end, and now if I displace the other end, then it goes back, of course. You know that. But if I displace it a lot, I simply bend it, I exceed some limitations of material, and it will never go back. So this shows that our expectations have to be a little bit moderated. We are considering displacements, but not too large displacements. There is a neighborhood, but now it's a three-dimensional neighborhood of this curve, of this stationary solution, which means it's like a tube. So there is some radius over here. Let's call it delta. And there is a three-dimensional tube. And I'm only interested in what happens when I displace my situation within this tube. If I displace it more, if I reach into the system and change it a lot, then okay, I don't care what happens. Okay? So that's the first limitation. We will be only interested in displacements like that. And the second limitation is that there could be some moment, some special time when the system behaves, let's say, in an exotic way. But I don't have to worry about it because stability means I'm looking at the development in time reaching to infinity. So if something is happening, let's say, on this part of time axis or on this part, I can simply ignore it. In other words, there will be a cutoff time. I will call it TS. And I'm only interested in what is happening after this time. I don't care about what's happening to the left. That's the past. I don't care. I look into the future. Okay? So these are two important limitations for my investigation. And now I just write it down mathematically. Let's see. Here we have a formal definition. We have a constant solution which solves a system, and you can see it's the general system, the one that we have over here. And we ask for the following condition so that we can say that the solution, the stationary solution, is asymptotically stable. And the condition is there must be some Ts, that's the cutoff time, and there must be some delta, which is the radius of this tube. In other words, that's how far we are allowed to move away from the stationary solutions. And then we demand that whenever we have a solution whose distance from our stationary solution is small enough, which is within the tube, at some time which is after the cutoff, so for instance this solution, this definitely fits, we are looking at time capital T, which is over here, and we moved within the delta. So this solution is one of those that we are testing. And what do we want? We want that this solution must converge to our stationary solution at infinity. So this is what we need for stability, asymptotic stability. And if this does not work, if there are some solutions that do not collaborate, then we have an unstable situation. Okay? How can we recognize it? That's a good question. Let's have a look at our situation over here. So we go back to Maple. And I have a little code here. I focused on the stationary solution 1,1 or equilibrium 1,1. And what do we have here? Well, we can see the stationary solution as dark blue curve, or rather straight line, or a rod in 3D. And I started with 1, 2, 3 different situations, 4 different situations. When I situate it like that, now you can see exactly the starting points. The green one, the whatever, gold one, and so on. Or perhaps it's the red one? Yeah, I guess it's the red one. Okay, how do I twist it back? This way. So, now the time is going to the right. And we can see that those 3D solutions are sort of circling around in space, but they do not seem to be going back to my stationary solution. Okay? This is really bad. I would be very pessimistic based on this picture. So I would say that the stationary solution 1,1 is unstable based on my situation, but there are problems. First of all, perhaps if I go in time farther to the right, then those interesting curves will go back, or perhaps not, I don't know. You see, this system is unsolvable. So what do you see over here? These are numerical solutions. So I cannot use analysis to say what happens when time goes to infinity. I cannot just calculate a limit or whatever. The second problem is, imagine that these curves will be actually going to my stationary solution. But that's just 4 of them. But I need all solutions on a neighborhood. Can I check on all solutions numerically? The answer is no, because I have to calculate each of them one by one using some numerical procedure. So the idea is quite clear, but we need to get some tools or some new insight into what's happening so that we can really judge reliably whether our stationary solutions are or are not stable. And for that, we will start with something that we know really well, which is linear systems. Here we have a very nice linear system, which is actually homogeneous, which is great. We know how such systems work. And I'm asking, are there any stationary solutions? So I'm actually asking for the right-hand side to be 0 as a vector. And that's something that we do in linear algebra, and we know that there is at least one solution, namely the trivial solution. All zeros. Definitely solves my system. So that's a stationary solution or equilibrium, depending how you look at it. Of course, there could be other stationary solutions, because if the matrix A is singular, then there is in fact infinitely many of them. But people really do not worry about it very much, because in applications, the matrix A is typically regular. And moreover, even if there are some other stationary solutions, we generally cannot really say very much about them. So people focus on the trivial stationary solution. And now we ask the key question, is it stable or not? Well, we have this stationary solution, which is actually just the t-axis now. Everything is 0, y1 and y2, throughout all the times. And stability means that when I look at nearby solutions, they tend to this stationary solution in a limit. So, why not the trivial solution is stable if solutions go to 0. But now here comes a trick. I'm not going to say for nearby solutions. I'm going to say for all solutions. How can we afford to replace one condition with another? I claim that actually these two conditions work exactly the same way for homogeneous linear systems. First of all, if all solutions go to 0, then also nearby solutions go to 0 automatically. So in one direction, the correspondence is quite clear. Let's have a look at the other direction. Let's imagine that we find that our trivial solution is stable, and therefore, according to definition, all the nearby solutions go to 0 in limit at infinity. Now, what happens to other solutions, those that are not nearby? There's a solution sitting over here, let's say, and it's too far, perhaps. Well, our system is homogeneous, and therefore solutions form a linear space, which means that if I take this solution and divide it by perhaps 100, I will get a solution which is near the origin. So it's small enough. And if it's not small enough, I divide by 1,000, by, you can imagine how it goes. So from this solution, I pass to a, okay, let me give it a name. I pass to 1 over 100, let's say, y. And because it's a nearby solution, and my trivial solution is stable, then this nearby solution must converge to 0. But if this solution converges to 0, then multiplying it by 100 still creates a solution which goes to 0. So this linearity business is very useful because the behavior around the origin translates automatically or extends automatically to behavior everywhere. So I don't have to worry about some neighborhoods. I simply look at all solutions and ask, do they go to 0? That's a much easier situation to handle. Moreover, going to 0 can be actually translated like that. I can ask whether the magnitude of my solution goes to 0 as a number for all solutions. And this is where it gets interesting. First of all, when you have a homogeneous linear system, you can simply write down the solution, look at it, look at the formulas, and ask, do all of them, all possible solutions, go to 0 or not? And that's a question that you can usually answer. No problem there. And we actually did it before. But let's get more sophisticated. What do we know about solutions? Well, all solutions of such a system are just a combination of some fundamental systems. So we have a fundamental system which consists of some vectors, let's say y1 through yn. And then we have a general solution, which is just a combination of these guys. Now, in order for the trivial solution to be stable, we need all solutions to go to 0, which means that also these guys in the fundamental system have to go to 0 because there are solutions. They are solutions by themselves. Conversely, if all the functions, all the vector functions in my fundamental system go to 0 at infinity, then their linear combination will be also going to 0. So this whole problem reduces to just my fundamental system. Do these guys go to 0 or not? Let's have a look at them. A typical vector function in my fundamental system looks like this. It's some vector and exponential, where lambda I is obviously an eigenvalue, and vi is an eigenvector corresponding to lambda I. Now, when I ask about the magnitude, I will actually have to find the magnitude of the eigenvector, because this is just a number, it can be pulled out. And then, when we ask about the magnitude of the exponential, we find that it does not depend on lambda as such, only on its real part. Because the imaginary part gives rise to cosines and sines, when we go to the real imaginary part, we don't have to really worry about it, because the absolute value or the magnitude takes care of it, and the magnitude of e to I something is always 1, period. So this is how the situation looks like for a typical vector in our fundamental system. If you are worried a little bit about this complex part, just imagine that lambda I is real for a second. Now, we want these vectors to go to 0. When does it happen? Well, this is a constant eigenvector. This doesn't change. T goes to infinity. If this exponential is to go to 0, then we need to require that lambda, or its real part, is negative. Otherwise, it will not go to 0. And we need this for all vectors in our fundamental system. Now, let's put it together properly. If your lambda is real, then you can ignore this real part, and you're simply looking at exponential, and the exponential goes to 0 if and only if the coefficient is negative. So far, so good. What if lambda is complex? Then we know that we are looking at real part and imaginary part, and it gets a little bit complicated because this vector may have some complex, it will have some complex components. Things will get a little bit complicated. But anyway, if we want our fundamental system to go to 0, then the real part must go to 0, the imaginary part must go to 0, and therefore this complex exponential must go to 0, and we are here, exactly in this part. So what we did was actually correct, even if we take into account this complicated situation with passing to real imaginary part and so on. The last problem appears if lambda is a real or complex eigenvalue with higher multiplicity. Then the solution is actually some combination of vectors, and also there can be some power of our variable, let's say power m. And the question is, what happens then? And again, we can take the AD norm, ask how large this is, and when we do so, we find that we are actually looking at the power times the exponential, again with real part of the eigenvalue in it. Now, what is the limit at infinity? We know this from calculus. exponentials are dominant. So the limit is simply decided by what happens to the exponential. If the exponential goes to infinity, so does the whole thing. If it goes to 0, so does the whole thing. So essentially, we get the same criterion. If we want to go to 0, we simply need this coefficient to be negative, period. And it works for higher multiplicity, for complex. It works always for all eigenvalues. And that's a general theorem which we can look at over here. And it says, if you have a homogeneous linear system with constant coefficients, then the trivial solution is automatically stable or asymptotically stable exactly if all the eigenvalues have negative real parts. And the proof actually can be done based on the analysis that we did over here. You just do it a little bit more carefully. If just one eigenvalue refuses to cooperate, then you've got an unstable situation, unstable stationary solution. So when you're investigating stability, you can go for it intuitively. You find your general solution and you ask, does it always go to 0 for all possible choices of A, B, C, whatever coefficients you're using? So on intuitive level, you can do it like that. Or you can simply look at your matrix, find the eigenvalues, and just by looking at eigenvalues, you know exactly what to expect. You know the stability of your trivial solution. And that's very handy, and it will come handy later on after we pass to more complicated situations. Before we do that, let me just recall something from past lectures, because we already investigated some systems, and one of them, the very first system that we had eigenvalues 1 and 3, and therefore the trivial solution should be unstable. And what I did, I actually plotted some solutions. And you can see them here. The trivial solution is dark blue, dark navy. It's the t-axis. And actually, it's not visible all that plainly, but OK. And the green curves, that's the solutions. And as you can see, they go away. So that's exactly what you can expect when your eigenvalues are positive, both of them. OK. The next example that we had was the complex case, when you hit cosines and sines and things like that. And this gets really interesting. So this is the situation when you have complex eigenvalues. The solutions, they look like that. It's very nice, isn't it? And let's say that we look at the gold one. Actually, that's the official name of the color, gold one. When I look at it from this point of view, I can see just one of the unknown functions. And as you can see, it's, well, in this way, it's negative cosine, but I have it upside down, actually, when I'm looking at the y2 axis. So let me just rotate it. Now the y2 axis is seen properly. So y2 is just the cosine function. And we can see it over here. Yeah, it's cosine. And then I rotate it so that I can see the y1 axis. So the y1 component of my solution is the sine function. And we can see it nicely. Okay? And the other solutions, they are just sine which is shifted for y1. For y2, it would be cosine which is shifted. So this is how things look like when we have a nice complex situation. And by the way, since the solutions are circling around the trivial solution, of course the trivial solution is unstable. And again, that's because the real parts were not negative. In this case, if you remember, the eigenvalues were plus or minus 2i. So that's a pure imaginary number where the real part is 0. And, well, 0 does not satisfy this condition. So we have instability. And finally, we had an example where lambda was negative 2, but it was of higher multiplicity, which is exactly this case. So when lambda is negative 2, double multiplicity, according to our observations, we should see stability. So again, I plotted some solutions just so that we can see what's happening. And as you can see, those solutions are approaching the trivial solution very nicely. And there are some, when you look at the y2 and y1, you will see exponentials. So that's exponentials for y2, and that's exponentials for y1. Very nice. Okay. So much for homogeneous linear systems. And let me just show you one application. I got this equation from my friends working in electrical circuits theory. And they tell me that it describes circuits that feature resistors, capacitors, and coils, essentially. I will talk about it more in my lecture on applications. Right now, we are not really worried about that. We are worried about the fact that this is a linear differential equation, and it's homogeneous, and therefore it does have a trivial solution. Is it stable? That's a good question. Now, just out of curiosity, I stands for the current which is flowing through the circuit. So when you have a circuit, some, those little bugs with little legs which are soldered onto a plate, and there are some wires connecting them, whatever, perhaps some battery or whatever. If you have such an electrical circuit, when it's switched off, there is no current happening, and yeah, it's okay. That's definitely one of the solutions. But what happens if you put some electrical energy into it, let's say some charge on the capacitor, whatever, and there is some current circulating around? What happens when you go to infinity? That's a good question. Stability of such a solution means that all the situation in all possible settings for the system, eventually the current goes to zero. Which is interesting. So does it happen? Question mark. Is it stable? Well, we do not have really the notion of stability, or we didn't look at it, for linear differential equations of higher order. So what do? I change it into a system. I take the derivative of I and give it some name. Derivative of I could be, let's say, J. I suspect that people from physics, from electrical circuits theory, they would have a different name perhaps for it and perhaps some story about it. I'm a mathematician, I don't care. Derivative of I is J, good for me. Okay, J prime plus R over L J plus 1 over LC I is 0. And let's rewrite it. So the proper form is I derivative is J, J derivative is minus 1 over LCI minus R over L J. That's the system that I'm looking at, and it has the obvious trivial solution, I is 0, J is 0. How about stability? Well, for that I have to look at the matrix, first of all, and the matrix of the system is 0, 1, minus 1 over LC, and minus R over L. And now I look for the eigenvalues. So I'm checking on the determinant of the matrix minus lambda 1 minus 1 over LC minus R over L minus lambda. How much is it? I have to take the product here, I pull out all the minuses, and it becomes lambda squared plus R over L lambda, and I subtract this product, and it ends up with plus sign. And I'm asking, could this be 0? Well, let's see. We have a formula for lambda. In the denominator, twice this coefficient, which is just 1, so it's 2 over here. This guy is put here with minus, plus or minus square root of, do I care? No, I don't. There is something here. And all I care about is the real part. That's the point. When I'm asking about stability, I just look at the real part of my lambdas. What do I see? The real part is over here. It's minus R over 2L. Now R is the resistance or whatever. These are physical constants. The important thing is they can never be negative. They are both positive, R and L, or perhaps 0 for R. So I know for sure that this is less than or equal to 0. And now there are two distinct cases. When R is 0, then the trivial solution is unstable. So the current can flow indefinitely. R is the resistance. So if there is no resistor in the circuit, I put in some charge, some electrical energy, and it will just be going around essentially forever. However, if I do put some resistor into my circuit, then the resistor will be sucking out the energy of the system and it will disappear. In all the situations, the current will eventually go to 0 in limit. So the trivial stationary solution is stable. Wow, that was easy, wasn't it? I mean, it's nice to have some theory and some understanding of stability. So that's this nice example. Well, it was going really well. So let's extend it. How about non-homogeneous systems? That's a good question. Derivative of y is ay plus b. Now, when we looked at these systems in general, we also included the possibility that the right-hand side b involves the variable. But here it will turn out right away that this is not a good idea. Why? Okay, I'm looking for a stationary solution. Stationary solution must have 0 here. So, ay plus b is 0. That's the equation I'm looking at. And let's just imagine for a second that there's also the variable t present in the right-hand side b. If I do find a stationary solution, then b will be minus a y naught. Now, a stationary solution is a constant vector. A is a constant matrix. This is a constant vector, and therefore b cannot involve any t in it. In other words, when you see a non-homogeneous linear system where the matrix is constant and the b, the right-hand sides, are not constant, then there is no stationary solution. Right away, you know it. So if you want a stationary solution, you want b to be a vector of numbers. And then if A is a regular matrix, then definitely there is some solution. And we have it. This is our stationary solution. What if A is singular? Then there could be infinitely many stationary solutions or perhaps no stationary solution. But notice, if A is singular, then one of its eigenvalues must be 0. And therefore, if there is a stationary solution, then it's automatically unstable. And we are done. So that's nice. Anyway, let's go back to our nice situation. A is a regular matrix. We found a stationary solution, and we can take it as the particular solution. So the general solution has the form y is equal to y naught plus yh. Now, when is our stationary solution stable? Well, it is stable if all nearby solutions go to it. But now, all the nearby solutions look like this. We have y naught, that's our stationary solution, and some solution of the homogeneous system. And now we see easily that we have stability for y naught if all the yh's go to 0. So this is exactly what we were investigating for homogeneous systems, and we know what to do. We look at the matrix A, we find the eigenvalues, and we want the real part of all the eigenvalues to be negative. The same criterion, the same theorem also applies to non-homogeneous systems where the right-hand side is constant. That's very nice. Okay, can we extend this to even more general situations, for instance, like this one? The answer is, well, not directly, because there is no matrix A. So without matrix A, we don't have any eigenvalues, whatever. But perhaps we can take inspiration from the pictures, from the ideas. It's possible, but for that, we actually need a slightly different point of view at the solutions. We saw the solutions as individual functions. That was nice. We saw them as two-dimensional, whatever dimensional curves. That was also nice. But now the time comes to try yet another point of view. When we have a solution of a system, we can look at it in different ways. We started by considering it just a bunch of functions. That was quite okay. We did get some information that way. And then we switched to another point of view where we saw it as a vector function. But this is just not any vector function. It's a very special vector function because it has only one variable. And such vector functions are very often interpreted as parametric curves. And that's the third viewpoint, and that's a very useful viewpoint. Let's have a look at it closer. Before we get there, by the way, in applications, we rarely use y1, y2, and so on for our variables. Typically, these would be proprietary names depending on the application that we are really investigating. For instance, this could be, let's say, location and velocity, or it could be temperature and pressure of air, or whatever. Now, for my purposes, it will be nice to interpret this as a location, as coordinates. And typically for coordinates, we use x, y, and z in simple situations. So that's what I'm going to do now. I will rewrite the first example that we had today, and I will pretend, here we go, that the first unknown function actually determines the x-coordinate of some location at time t. On the right, we will have the function y2, which will be the y-coordinate. Now, here I should write derivative, but now x and y, they depend on time, and the time derivative is typically denoted by a dot. So this is what I would call a practical version of my original system. Instead of y1, y2, y1, y2, y2, I'm writing x and y. And by the way, there was this solution, which now reads xt is e to negative 2t, and yt is e to negative t, t greater than or equal to 0. And I'm going to interpret this solution as a parametric curve describing the movement of, let's say, of a bug on my desk. Okay, so here is my desk, which is a two-dimensional object, because I'm looking just at the surface. And it's natural to consider coordinates x and y. Now, when this movement started at time 0, the bug was sitting at position 1, 1. Yeah, that's nice. That's a nice interpretation. Let's have a look at the corresponding graphs. I have them somewhere here on the top. Well, where was it? A long time ago, here. That was my first graph. So, at time 0, the x-coordinate is 1, the y-coordinate is also 1. How about time 1/2? Why not? Okay, so let me make a little note. This is when time is 0. Okay, at time 1/2, it would seem that the x-coordinate is something like 0.15 perhaps. So, well, it's about here, I would guess. And the y-coordinate could be something like 0.4, which is over here. So, when time was 0.5, the bug got here, which is quite a long way, so perhaps I should look at 0.25. 0.25, well, I see it somewhere over here, roughly. So that's the location when time is 0.25. And at time 1, x is almost 0, and y is approximately 0.2, somewhere here. So this is when time is 1. And of course, there are these intermediate locations. So when I look at my solution, I see it as a recording of a path that a bug took. And I see the trajectory. So if I take the bug and dip its belly in ink, carefully, I do not want to hurt it, of course, and I put it on the desk, the bug is scrolling in this way, and I can see the trace, I can see the trajectory. And this trajectory obviously has something to do with the solution. It's the list, or let's say it's the amalgamation of all the locations that the bug went through. In other words, it's the amalgamation of all the locations that this solution came through. Let's have a look at this. I have the 3D graph here of my solution, and now, where do I see the locations? For different times, I can take a slice which is perpendicular, which is parallel to x and y axis, or y1 and y2 axis in this picture, and I simply, okay, I can see a virtual desk over here. Perhaps let me sketch it. This is x, y now, and I can see the virtual desk over here. And then I take this virtual desk and I slide it to the right along the time axis, and it intersects my solution. Always. At some time, it intersects it here, and I can see the position of the bug. So all the positions are in those virtual tables that are moving along the time axis. And now if I look at this picture from this direction so that the time axis disappears, it goes away from me, I can see exactly the locations. And that's exactly the curve that I have over here. That's the trajectory that the bug took as it was scrolling across my desk. So this trajectory tells me something about the solution. it doesn't say all that much. When I look at the trajectory and I see it as a curve, just as a curve, without these remarks about times and so on, I see it just as a curve, mathematical curve. I'm losing information about many things. I do not see the bug's velocity anymore. And I don't even know at what times the bug was here or there or there. It's even possible that there are two bugs at different times crawling at different velocities along the same path. In other words, it could easily happen that I have two solutions, two distinct solutions. When I look at the trajectory they take, I will get the same trajectory. So I'm definitely losing a lot of information. On the other hand, this trajectory is useful because it's two-dimensional. I can draw it. I can draw many of them. And as we will soon see, I can actually draw them even if I do not know the solution. Anyway, this is very useful. It deserves a name. And as usual, in the field of differential equations, we have a grand name for it, something that looks really nice. So when you have a solution and you look at the set of all locations for some time interval I, you call it an orbit. So this would be an orbit of this solution. How do we find orbits? Well, if we know the solutions, then it's actually fairly simple because this is just a parametric curve. And in calculus, we learn that, well, the parametric curve can be determined by eliminating the parameter t. So let's have a look at it. X is e to negative 2t, y is e to negative t. How do I eliminate? Well, actually, in this case, it's fairly simple. I just write this as e to negative t squared, which is y squared. So this curve that we can see over here is given by formula x is equal to y squared. It's a piece of parabola. So just by doing that, I can draw this piece of parabola over here. I can denote that this is the starting point for the bug, and that would be the orbit. But we are really losing a lot of information. So what people typically do, they do not just consider orbits, but they consider oriented orbits. I would add an arrow over here indicating the direction which the bug took. Definitely. Also, one should be a little bit careful because the parabola also extends over here. And when we look at the solution, it's clear that the bug does not really cross the origin. It actually approaches the origin in limit at infinite time. But when you solve it like that, you may think that the bug was going this way. So one has to be really careful when interpreting. Well, after all, we have the condition that y is never 0. So at this point, there can be no solution. Definitely, this should be an empty point. Y different from 0. Okay? So now we are getting more information. By the way, we have a solution. We eliminate parameter like that. We get the description of the orbit. How do I find the direction of travel? Well, when I look at my equations, I can see that they are actually telling me how x and y change. So I look at x. X is the x-coordinate. And this is the time change. And the time change is always negative. So x is always decreasing. It depends on the location where the orbit is going. But here, it doesn't really matter. Always negative means we always move to the left. So this is the right direction. Or you can look at the second equation and you can argue, okay, if I'm here, then x is positive and y is positive. Okay, let me add it here to be proper. In this quadrant, x is positive, y is positive. This ratio is positive, negative. Y derivative must be negative, so y is getting down, it's decreasing. Yeah, we are getting down. Yeah, it fits. So knowing the solution, knowing the system, we can actually draw the orbits. Now it gets interesting. I said that I know the solutions, but let's imagine that I don't know the solutions, okay? So here is my desk, and I'm asking, okay, how are the bugs behaving, depending on where I put them? Well, let's have a look at the first equation. It doesn't really matter where I put the bugs. They always move to the left. So let me just make a little remark here. Bugs are always moving to the left. How about the vertical direction? I can see it in the second equation. The vertical direction actually depends on this factor. And I can see that this expression changes signs. Well, we did something like that before, didn't we? When we are doing the vector field or slope field. We look at the right-hand side and we ask, okay, what are the signs? Where are they changing? When they are changing? Well, x over y, there are two possibilities for the sign to change. One of them is when x is 0, and the other possibility is that y is 0, because then the expression does not exist, which is a nice opportunity to change signs. And these are the dividing curves for the sign of y dot. Where do I see them? Well, these are the coordinate axes. They split the plane into 4 regions, 1, 2, 3, 4. And in each of them, this expression has a common sign. Which one? Well, let's have a look at the upper right region. X and y positive, overall negative sign, y is decreasing. We are going downwards. So we are going downwards. Well, let me put it here. But we are also going to the left. So it means we are going southwest, essentially. So when the bug is somewhere here, it's going down like that. And this tells us something about the shape of the orbit, or at least the general tendency of the orbits. What happens if we are sitting in the lower right quadrant? X is positive, y is negative. X over y negative, overall positive, we are going up. We are going up, and we are going to the left. That's the general information here. So we are going northwest. So all the bugs that are here are moving in this direction in some way. And in this way, we can go through all the quadrants. And you can notice that the ratio x over y is the same in these two guys. So we should get the same information and the same information here. So this is something like a slope field, but it's not for the solutions, because the solutions are 3D curves. This is a slope field for the orbits, for the locations, for the trajectories, which is something different. As I said, not enough information. But on the other hand, by losing some information, we arrive at a, let's say, simpler situation, which can be handled like that. We can do analysis for the orbits. We cannot do it for solutions, unfortunately. So that's the main advantage of orbits. They are not perfect, definitely not, but you do get some information. Notice the following thing. We are getting information about the change, how fast x is changing and how fast y is changing. So we are getting information about velocity or about intensity of change in the two basic directions. What happens if x changes a lot and y changes just a little bit? Well, then it means that the bug is moving in this direction. So you can actually use the information about x derivative, which you can see over here, this is time derivative, and y derivative, and compose them together like that to get the direction of the bug. You do not just need to, use up and down, left to right, but you can actually give a more detailed situation. By the way, what is the slope of this direction? Well, perhaps this picture will be nicer. If x is positive, x derivative, and y derivative also, then the slope here is y dot over x dot. And this should ring some bells. What is an orbit? Orbit is a parametric curve. A parametric curve exists in space, and as a curve in space, it must have spatial derivative, which we can denote dy over dx. And the formula from calculus tells us that for a parametric curve, this is dy over dt divided by dx over dt. And if I use my notation that I have over here, I can write it as y prime is equal to y dot over x dot. This fits perfectly with the theory that we have. But from the practical point of view, this is what a computer can do. You pick a location and you ask the computer, take this location, substitute it into the formulas, into your equation, in fact, into the right-hand sides, and you will get the magnitudes of these two vectors. And use them to find the right direction, and please, pretty please, plot it. And do it for many points. And what you get is this. That's a beautiful picture. In general outline, it does agree with our sketch. lower right quadrant, we are going northwest. Yeah, that fits. Southwest, northwest, southwest. So the general overview fits, but we can see in more detail what is happening. Can we see the parabola there? Yes, I do sort of see the parabola there when I'm following the arrows. Okay. What's happening down here, lower right quadrant? I do see the parabola too, but we are moving in a different direction along this parabola. So if I put a bug over here, it will be crawling towards the origin like that. Interesting. But it seems that if I put the bug a little bit more to the right, it will be crawling like that. Interesting. Over here, if I put a bug over here, it will crawl this way or perhaps this way. I don't know. Actually, y is not allowed to be 0. So there should be an empty circle. We are getting really, really interesting pictures. If I put the bug down here, or up here, perhaps, it will be crawling to the left like that, it seems. So based on this sketch made by a computer, I guess we can call it slope field for orbits. We can actually see what kinds of different paths the bugs can take depending on where I put them on the table. Do I see the solutions? The answer is not quite, but I do see a lot. A little side note will be very useful at this moment, I think. We encountered slope fields before, namely when we were investigating just one differential equation, something like that. Y prime is equal to f t y. And the pictures produced by Maple were sort of similar to those that we have now, and also the pictures, the sketches that we made were similar, and actually the methods that we used, the procedures, were also analogous to what we just did. However, there is a deep fundamental difference. When we have just one differential equation, then the solution is one-dimensional, and we have access to its graph, which means that we have the value axis, here is the independent variable, I will read it as time for the moment. And when we have a solution, it tells us how this quantity, which is what we are interested in, how this quantity changes in time. So that's a complete information. Now, time, or any other independent variable, has a default direction. We always see it flowing left to right. And therefore, when we sketch the slope field, the arrows always have to go left to right. The only choice they have is whether they go also up or down. So the only arrows which we can expect are going northeast or southeast. And no other arrows are expected or possible when we look at a slope field for just one differential equation. On the other hand, when we have a system which we write like that, and we have this nice correspondence, then the solution is more dimensional, let's say two-dimensional, which means we cannot see time in our picture, we just see the values. And when there are more values, we need more axes, coordinate axes to show them. So for instance, when we have a 2x2 system, then we actually need two axes to show us the values. And that's why there is no room for showing time. And we get orbits. Now orbits, that's the quantities, how they change, and there is no default direction. The orbits can go any way they feel like. This can be an orbit. So there can be this direction, northeast, or northwest, or southwest, or southeast, and so on. All kinds of directions, everything goes. Which is exactly what we see in our picture. There the arrows go to the left, which would be impossible if we were sketching slope field for a solution. But we are sketching slope field for an orbit, which is a different story. Okay, so there is a big difference. Just out of curiosity, the definition of orbit makes sense for any dimension. Also here, what is an orbit? It's the set of values. We see the values over here on the y-axis, so the values that we can achieve are here. With one-dimensional solution, the orbit is just a one-dimensional set, perhaps an interval typically. And we don't know when these values are achieved, which is exactly the problem with orbits. We are losing information about time, about velocities. We just know that these values were achieved by our solution. So that's not a very good information, and that's why orbits are never used for just one equation. When we pass to higher dimension, then again we just see the values. We are losing information about velocities and so on, but there is an extra information because these two quantities, they are somehow interdependent. There is a relationship between them which is given by the system. And when we look at an orbit, we can actually see what is the relationship between the values which are allowed for x and y. So in more dimensions, the orbits actually carry more information than one-dimensional orbits. There is something to be seen, and that's why orbits can be useful. Although, as I said, we are losing a lot of information, there is still enough left to make it interesting. Okay, that's enough for the side note. Let's go back to business. That was really nice. And we will definitely want to try this also with our second example. But before we do that, let me show a little bonus. This key formula connects information about spatial derivative of y as a curve and the time derivatives of the coordinates. So, the spatial derivative is, and now it gets interesting. For the time derivative of y, we have a formula here in the differential equation. So I just copy it. It's minus x over y, and it's divided by negative 2y squared, which is the time derivative of x, which is, by the way, okay, I see it as x over 2y cubed. Now, I need two pieces of luck. The first piece of luck is that my system is autonomous. There is no t in it. Because if there were t in it, that would be the end of the road. But it's not. And now I look at it and I see function y, which depends on x. I see its derivative with respect to x. And I see a formula with x and y. This is a differential equation, ordinary differential equation of order 1. And that's where the second piece of luck comes in. Can I solve it? That's a good question. This one is actually, it looks separable. Let's separate. I will move 2y cubed to the left, and I will multiply everything by 2 to make my life easier. 4y dy over dx, and y is cubed, is 2x. Okay, I distribute the x to the right, which I'm not allowed to, but okay, let's just write down the integrals. And now it looks okay. So that's the integral on the left. That's the integral on the right, and now you can see why I multiplied everything by 2, because I was predicting integration here. So y to the power 4 is x squared plus c, and that's exactly the description of my orbits as spatial curves. If you want, you can try this. Y is plus or minus 4th root of x squared plus c, and one sees that one should start worrying about the existence. Anyway, that's a formula describing a parametric curve, but now it's in the form of an implicit function. And there are ways to sketch implicit functions. I can ask Maple for that. I asked it to sketch some implicit functions, and you can see them over here. And this generally fits with the shapes that we were seeing. Okay? So if you get really lucky, you can actually get the precise shapes for your orbits by solving an ordinary differential equations. But you have to get really lucky. So we are not going to rely on that. We are going to rely on this analysis of directions. Or perhaps we can ask some computing system to get more precise information about shapes. So let's apply this to our second example, because that one was more interesting. I wrote our second example again with x and y as the names of the functions instead of y1 and y2, but otherwise it's the same formulas. And let's investigate how the signs of x and y change depending on the location in the xy plane. So we will start with the signs of x. So x dot is y squared minus 1. When do the signs change in the expression on the right? Well, the dividing curves are obviously 1 and negative 1. But now we have to treat them as dividing curves in 2D in the xy plane. So here we go. X, y. 1, negative 1. Y is equal to 1, that's this horizontal line. Negative 1, that's this horizontal line. And they split the plane into 3 strips, horizontal strips. Now, if we are in the top strip, then y is definitely more than 1, and this expression is positive. So the derivative of x is positive, and therefore x is increasing. We are going to the right. everywhere here. The same is happening in the lower strip, because y is negative, but smaller than -1. So in absolute value, it's bigger than 1. Again, derivative of x is positive. We are going to the right. In the middle strip, y is small, for instance 0. So this is negative. X is decreasing. So x is getting smaller. We are going to the left in this strip. So that's the left-right direction of our orbits, of the travels, of the trajectories of the solutions. Okay, that was the x part. Now the y part. Y part is over here. Y dot is y minus x. Could it be 0 or perhaps not exist? I should ask, is it possible that this guy does not exist? And the answer is never. Okay, the same thing here. This exists always. So we are just asking, could it get 0? And the answer is yes, when y minus x is 0, which is the curve y is equal to x. There's just one dividing curve, x and y. Now, if we stay in this upper part, which is like triangle, perhaps, infinite triangle, so if we stay in this upper left part, then y is, let's say, infinity and x is 0. So this will become positive. Y derivative is positive. Y is going up. It's increasing. So everywhere in this triangle, we are going up. If we are down here in this lower triangle, then y is, let's say, negative infinity, x is 0. I'm getting a negative sign here. Or you can reason it out in some other way. We did this for ordinary differential equations. So this is actually standard. We have two influences, horizontal influence, vertical influence. Now we have to merge them, overlap them, or overlay them. That may be a better word. So here we go. Okay, where do I want to see one? Perhaps somewhere here. -1, -1. Now there's this horizontal dividing curve, which is the horizontal line. Another dividing curve. And now the oblique, diagonal. Oblique diagonal. Here we go. The intersection should be 1, 1, -1, -1. And 1, 2, 3 curves. They divided my plane, my xy plane, into 6 regions. And for each region, we have to put the information together. So upper strip, upper triangle. We are going right and up. Right and up. We are going this way. Okay, this little triangle over here. We are in the upper strip, but below. So we're going in right and down, right and down, right and down. Okay, middle strip, we are going left, but how? Below the diagonal, we are going down, left and down, left and down. We are going this way. Above the diagonal, but in the middle strip, we are going up and left. This is becoming really interesting. Okay, lower strip, we are going right and down, or right and up. This is too small. Let me extend it a little bit. Okay, I think it's better now. So, that's how the trajectories go. You take a bug, you put it somewhere, and it goes according to the arrows. This looks interesting. I will ask a computer what it thinks about it. Okay, this is our system. Derivative of x is y squared minus 1. Derivative of y is y minus x. That exactly fits. And I will ask for the slope field. And yeah, it sort of fits with our picture, I guess. Yeah, here we can see left down, right down, left down, right down. Yeah? Here we can see the strange thing, we are going away, and, well, this is interesting. Yeah, there are some interesting things happening. Here we can see turning up, up left and up right. I can see it over there in the arrows. So this is definitely a good differential equation. I mean, the good system of differential equations, because this is much less boring than the first example. By the way, can we identify the shapes of the orbits? using the trick, the bonus that we had before? Well, let's try it a little bit. The spatial derivative should be the derivative, the time derivative of y, which is this formula, divided by the time derivative of x, which is this formula. Well, is it separable? No. Is it linear? No. Is it homogeneous? No. Integrating factor? No. Actually, no method works. This equation cannot be solved analytically. That's the dead end. We were not lucky. We do not know the shapes of these orbits. Interesting. Now, we looked for the stationary solutions. That's a good question. How do stationary solutions look like if I'm just looking at orbits? Well, remember, orbit is actually a trajectory. If a bug belongs to a stationary solution, or if it's governed by a stationary solution, then it just stays in place, it doesn't move. So stationary solution have orbits which are just points. Now, for our example, we found two stationary solutions, and we can see it again. I take the right-hand side here, and I want it to be 0, so y can be 1 or -1, and this should be 0, so x must be the same as y. Yeah, very simple. So we can call them equilibria now. Two of them, 1, 1, and -1, -1. How do we recognize stability? That's a good question. Well, stability means that nearby solutions should be going in limit to our stationary solution. When I look at the trajectory, there is a stationary solution here, and I put some bugs around, and I follow the development in time, and I want the bugs to go to the stationary solution. I want them to go, the orbits to go to this equilibrium. So let me put a little remark here. The stationary solution is stable if and only if nearby orbits go to, okay, let me give it a name. Stationary solution, why not? And that's another advantage of orbits. First of all, I can visualize them like that or like that. And second of all, I can use them to decide stability. So let's have a look at our field or vector field, slope field, whatever, for our stationary points, for our equilibria. Equilibrium 1, 1. Well, what if I start nearby? Where will I go? Well, actually, I'm not going towards the stationary point. I'm going up and right. This is interesting. I'm not going there, but perhaps I can, well, it doesn't look that way. I would have to go towards, but none of these arrows actually goes towards the stationary point. So I look at it and I say, okay, this looks pessimistic. That's the way I see it. I don't think this one is stable. How about here? Well, here is my stationary point, and if I move a little bit away, I should be going up and, yeah, I will never go back. Perhaps yes, later on. So I don't really know, but it looks really, well, I'm not really sure. I mean, if I look at the neighborhood, I would say that I'm going away in this direction. So I would say this guy is unstable, but I don't know what happens later. That's a little problem. So, well, because as you can see, this arrow sort of goes towards this equilibrium. So if I go around and I come here, perhaps I'm approaching it or not. Let's have a look at some details. So this picture should be the detail of the upper right quadrant. We should see it bigger. The dot in the middle, that's the point 1, 1. And we can see those arrows, they are sort of moving around like a fan, and they seem to be going outwards, not inwards. So I'm pessimistic, I'm very pessimistic. And this is the second one, -1, -1. And you try following some arrows, and you can see that they're flowing sort of around, but you are never getting there. So this is also quite pessimistic picture. Yeah. So I would say this does not look good. This looks, in fact, quite bad for these equilibria. I don't see them as stable, but I'm not sure. So can I get something, some more precise information, something that I could rely on? And the answer is, well, to get there, we have to go back to linear systems, because there we know what's happening. Okay, we have a homogeneous linear system with constant coefficients, And therefore, we have a stationary solution, namely the trivial one. What is happening around this stationary solution when we look at orbits of solutions? So here we go. The stationary solution, now seen as an orbit, is just the origin. Okay. What kind of solutions do we have? Again, we have to start with the fundamental system. So the prototypical solution looks like this. Y is some vector times exponential. Let's just imagine for a second that lambda is real. Okay, so these are the locations as they depend on time. And when we look at it, the only two-dimensional or three or four-dimensional, now you can imagine in 3D or 4D, whatever. The only more dimensional thing is this vector. So let's say that the vector goes this way. This is the vector v. And all the locations are based on this vector. We are just multiplying it by some number which could be, well, positive but large or small. So all the locations are along this ray. If at time 0 we are sitting here and the time starts increasing, then everything depends on lambda. If lambda is positive, then the exponential grows, and we are moving in this direction. So this is the orbit for lambda positive. It's a ray going away from the origin, and this means that the stationary solution 0 is unstable. If lambda is negative, then e to lambda t goes to 0 for increasing time, and we are in fact moving towards the origin for lambda negative. And for this particular solution, this looks hopeful. We would get perhaps stability. At least we didn't destroy it or spoil it. That's the good news. What happens when we have a solution and lambda is complex? That's a good question. Well, this is not so easy to see. It requires a little bit of work, but there are two solutions. One of them is the exponential based on the real part of lambda, and the other one also has it. And then we take the real part, or the imaginary part, of the vector v multiplied by exponential, which uses the imaginary part of lambda times I times t. E to imaginary part of lambda I t. And as I said, this requires some experience. This is not as transparent as here, but the trick is that if we plot the vector v, let's say here, that's the vector v, then this part, the real part or the imaginary part, they impart rotation. And this part is something like a radius of the rotation. So when lambda, or the real part of lambda, is negative, then this exponential goes to 0, and we get a spiral which is going towards the origin. So this is for real part of lambda negative. And again, you can notice that this does not spoil stability of the origin as a stationary solution. So real lambda negative, real part of lambda negative, which is the same here, are good for stability. If real part of lambda is positive, then this blows up, it goes to infinity, and we get a spiral which is enlarging, 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 getting bigger and bigger. This is for real part of lambda positive. And we have unstable situation right away. We don't have to investigate anything more. What happens if lambda is 0, by the way? Then this is constant 1, and we get just a dot for the orbit. So it's a stationary solution. What happens here if real part of lambda is 0? Well, we get something which is cyclic. We get an orbit that is like an oblong something, ellipse or whatever. Okay? With a bit of luck, we get a nice picture, we get a circle, but of course we cannot expect that, and there is no reason really to expect that. So these are the situations for the individual parts, individual vectors in our fundamental system. Now what happens if you start combining them? Well, there are some clear-cut situations. Let's have a look at them. The first clear-cut situation is when all the real parts of lambda are negative. What does it mean? Well, it means that all the orbits are going towards the origin. It doesn't matter whether you do have or do not have some imaginary part, your orbits are going to the origin, which is good for stability. Okay? Let's start with this part. Imagine that all the lambdas are real. So the imaginary part of lambda I is 0 for every I. Then all the vectors in our fundamental system are going to the origin along some ray, but then you start combining them in linear combinations. Again, this is not something that you can see easily, but with a bit of experience and some experimentation, what happens is that you are really approaching the origin from different sides, from different locations, but not along straight lines, along rays, but this will be some curving movements. So for instance, it can go like that, or like that. That's a typical situation when all the eigenvalues are real and negative, you get something like that. And obviously, such a situation is stable. The origin is then a stable stationary solution. The other obvious case is when you have those real parts negative and you have some imaginary components. What happens then is that you get this turning notion, and you are still going inside. So you are going towards the origin, but you can start at a different place, of course. And again, that's a nice situation because it's stable. That's the important thing. And everything else is unstable. Okay? Now, what happens if some eigenvalues are real, some are complex? Well, this actually cannot happen in 2D, but in more dimensions it can happen, and then you are perhaps circling in just one plane, and in the third direction you are going directly, so to speak. You know, things can happen in interesting ways. The other obvious case is when all the real values of lambda I are positive. And then essentially the picture is almost the same, just all the solutions are scared and running away. So obviously this is an unstable situation. And here we have the same thing. And all the solutions are running away, but they are running away along a spiral. And this one perhaps in the other direction. I don't really care much, okay? So is that actually possible? I don't think so. So perhaps the picture is not quite okay. It's just an unofficial picture. I'm just, fooling around. There will be an official picture soon. So these are the four, let's say, obvious situations. Unstable. But then there are many more situations. For instance, one of the eigenvalues can be 0, another one complex, another one real, which is not 0, and so on. Those situations can get really, really interesting. And let me just show two more interesting boxes. One interesting box is that there is one particular eigenvalue which is positive, and another eigenvalue which is negative. That's a very interesting case. And this actually means that they are real automatically. So here is my plane, here is my origin, which is the stationary solution. Now, this eigenvalue has eigenvector coming with it, and in this direction, we are moving away. So if you choose a solution which is just a multiple of this eigendirection, of this corresponding solution, then you are going away along a ray. This lambda has eigenvector coming with it, and you are moving inwards along this direction. What happens if you start at some other place? That's a good question. And then the answer is, well, those two tendencies combine. So if you start here, first this one pulls you towards the origin, but then this one takes you away. And the same is happening here, and here, and here. This is a very nice shape. Very interesting. Of course, it's unstable. That goes without saying. So that's one interesting case. And another interesting case is when you have real part of lambda i's 0 for every I, and there is some complex eigenvalue in play. So there exists lambda I complex. And then you get essentially a periodic solution, which is also very interesting. And as I said, there are many more possible cases, but they are not as nice and not as useful. This is so-called classification of stationary solutions or classification of equilibria. And these situations, they have their names. Let me show you. And I actually don't think there is any point in memorizing them. So what we can see here is, does it correspond? Did I get it right? Yeah, I think I got it right. Okay. So in this case, the stationary point, not the solution, not the orbit, but the stationary solution is called a center if the solutions are circling around. Here, the stationary solution is called saddle. So this is classification of equilibria. These two equilibria are called nodes or knots, and they're stable, unstable. Yeah, makes sense. And these guys are called foci. I think that's the plural. Focus, foci. But if I say focuses, probably it's okay as well. Okay, so that's the basic classification. When people in applications come up with some system of differential equations, they analyze them for their stationary solutions because they are really important in applications. And then they want to see the classification because these basic shapes, they actually also appear in nonlinear systems. These are the names that are general, and we want to see them. We want to see how these things work. And for that, we will have to work some more. But to conclude this part with linear systems, let me go back to Maple, and let me revisit what we did before. So I have recalled 3 examples that we covered in this course for linear systems. The very first example has unstable stationary solution. We can see that the solutions are flying away. And now let's turn it so that we can see just the locations. These are just the locations. And we can see that the orbits are going away, like rays. One of them is curved, the other guy is not. Yeah, it can happen. These two guys are probably these exponentials times v from the fundamental system. So I think I took 2 solutions from the fundamental system, and the third one is their combination. So you can see how it works nicely. In the second case, this was the complex eigenvalue, purely complex, just 2i, plus or minus 2i. So that would be exactly this case. The real part is 0, and there is some complex component. And you can see that those 3 solutions are doing nice ellipses. These actually are ellipses. So that's this case. So for this particular system, I would say that the trivial solution is a center. For the previous one, I would say it's an unstable knot, for instance, or node. And then there was the third example where we had stability. That was the case with real eigenvalues which were negative and of multiplicity 2. I think it was negative 2 with multiplicity 2. And now when we look at the orbits, yeah, I think, well, where am I? Now we can see the orbits. And 2 of them, well, are almost straight, but they're not straight anymore because there is this t also appearing in the formula. So the 2 guys, they are parts of the fundamental solution, and the third one, which is curving, that's actually a combination of these 2 guys. And you can see that they're approaching 0, so that would be the stable knot or stable node. So this really seems to work. And it brings us to the problem of doing this for general systems. So let's go back to our beautiful example. Here it seems that we are going around, but not all the way around. I don't see like ellipses. We are moving outwards and spinning. So I would say this is unstable focus. That's 1-1. 1-1, unstable focus. That's my guess. And over here, when I look at this, that was the stationary point -1, -1, and we seem to be going like that, which is exactly this situation. I would guess that this is a saddle. But the problem is, this comes from a system 2x2 system which is not linear. So again, I don't have any eigenvalues. Can I confirm it? Can I find a way to discover it without drawing it? And that's the last topic, and a very important topic. So let's make a lot of room. And now for the ultimate challenge. We have a system, first order system here, which is almost general. Notice that there is no t in the right-hand side. So this is an autonomous system of differential equations. But other than that, we can expect anything on the right-hand side. In fact, we can expect that this system is not linear to make our life more interesting. We want to find stationary solutions and then classify them, because there are 6 types that we are really interested in. How do we do it? Well, stationary solutions, these are found easily. We take the right-hand side and make it equal to 0 as a vector, because this is a vector, the output is a vector. Now, the fact that f is most likely not linear makes this situation very interesting, because there could be 1 solution, or no solution, or 13 solutions, anything can happen. The fact that the system is autonomous, that there is no t in the equation, actually makes it more likely that we do find some stationary solutions. So let's be optimistic. Let's say that we found some and we pick one of them. Here it is. Ys, for stationary, obviously. That's a stationary solution. But perhaps we can call it a stationary point, because now we are adopting the point of view of orbits. Okay? And now, classification. We want to know what's happening with orbits around this stationary point. Or, in another way, we want to know what's happening with solutions around this stationary solution when we see it as a constant function. Of course, we could, sketch the vector field using this right-hand side. We did this before, and it did send some, messages, but they were not reliable. That's the problem. So we need something which is mathematical, reliable, complete information. Well, to get there, we look at this equation again and we ask, what is the story behind it? And well, there may be more stories, but there is one which I'm interested in right now. It's a feedback equation. You have some quantity that you are really interested in. In fact, you have like n quantities, but we lump them together into one vector. So let's say you have one quantity, multi-dimensional quantity, and you want to know how it changes, how it behaves, how it develops. And the equation says, if you want to know how this quantity changes, you just look at it right now. That's the current situation. You put it into this formula f, and you get your feedback. You get information how your quantity changes. Now, when we are doing classification of a stationary point, we are not really interested in the general behavior of solutions or orbits. We are just interested in what's happening when we are nearby, which means when y is close to ys. And that's a familiar situation. We want to know how some function works near a specific point, and we are not really happy with the function because it's general, it's complicated. So we replace it with its approximation. Let's say a linear Taylor approximation. That's a good idea. That sounds really good. So what happens? Well, we have this derivative, but instead of equality, I'm going to put this really imprecise approximation mark, and I replace this function with its Taylor expansion. So there's this absolute term. I'm putting ys. That's my chosen center for the approximation, for the Taylor expansion. I'm putting it into f. And then there will be this, in quotation marks, derivative, which in this case is the Jacobi matrix, again at location ys. And this multiplies the vector y minus ys. So this is really like a Taylor polynomial for ordinary function, just moved into more dimensions. Now, if this function of f is not too wild, then this approximation and the original function should essentially provide the same feedback around ys. So it makes sense to replace them like that. And notice that ys was a stationary point for this right-hand side, and it is also a stationary point for this new equation that we have here, because fys is definitely 0, and when we put ys here for y, we get 0 as well. So this new system has the same stationary point, the center ys. This new system is called linearization of the original system. And that's a very important notion. Let me put it here. When we go from here to here, this is called linearization. And of course, it's just local. It makes sense to consider this linearization only when we are nearby this stationary point ys. But that's all that we need right now. Okay, let's have a look at it again. Y vector derivative is about, well, fys, that's a 0. We talked about it, 0 as a vector. So I split this into two parts. There will be the Jacobi matrix f at ys, multiplying y. Then there will be minus the Jacobi matrix at ys, multiplying ys. Now, Jacobi matrix at a specific location, that's a constant matrix. This is a constant stationary point, so this is a constant vector which we typically call b. This is our unknown function, and that's a matrix. And again, it has constant coefficients. It's a constant matrix. So we can call it A, and when I look at this, I can actually see a linear system, which is not homogeneous, perhaps. We don't know. This could be 0, for all I care. I don't really care. So, if I want to know how this stationary point works, how the orbits around this stationary points look like, how they behave, all I need to do is pass from the original equation into my linearization and ask, okay, what's happening here with my stationary point? And the answer is, the matrix A decides. I just look at the eigenvalues and I have my answer. And that's the whole secret. Let's try it. Our second example goes like this. The derivative of x, the time derivative, is y squared minus 1, and the y derivative with respect to time was y minus x, I think. That was the system. What is the feedback function? The right-hand side. The function takes values x and y and spits out the vector y squared minus 1, y minus x. Okay? No problem there. So, if we want to approximate this function at some center, we are going to need the Jacobi matrix. Jacobi matrix at xy looks like, let's see, I take the first component and I differentiate it with respect to x and with respect to y. So the derivative with respect to x is just 0, and the derivative with respect to y is 2y. So far, so good. The second component, again, differentiate with respect to x, with respect to y. So derivative by x yields -1, derivative by y yields 1. So that's the general formula for the Jacobi matrix of this particular function. Now, let's have a look at stationary points. Now, if you remember, we had two stationary points, point 1, 1, and point -1, -1. And if you want, you can try it again. You make this one equal to 0, and you get 1, -1 for y, and then you make this one 0, and you find that x is the same as y. Here we are. So, around the point 1, 1, we take this equation, and we replace the right-hand side with the Taylor approximation. We do this linearization. And what is the matrix in this Taylor approximation? What is this new system? How does it look like? What is the matrix A? Good question. Matrix A will be the Jacobi matrix at the location 1, 1, which is, let's see, well, we are putting 1 here. 0, 2, -1, 1. So that's what we call A in this linearization. What are the eigenvalues? Good question. Well, let's see. I find determinant of minus lambda 2, -1, 1 minus lambda, which comes to, okay, lambda squared minus lambda minus plus 2. And I'm asking, does it ever get 0? get to be 0. Well, let's see. Let's split it. This is a school problem, so I expect something nice. Lambda here, 2 at the end. So 1 here, 2 here. Either 2 minuses or 2 pluses. Okay, they do not work. So factorization didn't really help. I have to go to the formula. Lambda is, let's see, division by 2. Minus 1 is plus 1. Plus minus square root. 1 squared minus 8. So this will be 1/2 plus or minus square root of 7 over 2i. Actually, I don't really care very much. What I care about is, first of all, the real part. That's here. The real part is positive. What does it mean? Well, it means that the solutions will be going away from the origin, or in other words, when I shift the situation away from my stationary point 1, 1. So it will be unstable. This I can see right away. I can also see that the imaginary part is not 0, so there will be some rotation happening as well. Well, unstable focus. That's my conclusion. And in fact, we guessed it before. That was our guess. But we were not sure. And now we can be sure, because the linearization confirmed it. Let's have a look at the picture. Let me recall how the situation looks like around the point 1, 1. That's the picture that we had before. And when I look at these arrows, they do seem to go around in circle, but outwards. It's like a fan. It's a spiral which is unwinding. So yes, this picture, as I see it, it goes around to the right like that, clockwise. In my picture, it's counterclockwise over here, but this doesn't really make any difference. Okay? The tendencies are the same. It's unstable focus. Okay, now for the second picture, just out of curiosity, for -1, -1, we had this. That was the slope field. So there are those bending orbits going around, never reaching our stationary point in the middle. They seem to be approaching and then going away, and some of them are just going away. So going back to my classification, I would say that this is a prime example of a saddle. This looks like a saddle. Let's see whether we confirm it. So our matrix A for the linearization is the Jacobi matrix with -1, -1 as the center. I substitute, and I get -1 here. So it's 0, -2, -1, 1. That's my Jacobi matrix. Let's find the eigenvalues. Determinant of minus lambda, -2, -1, 1 minus lambda is lambda squared minus lambda minus 2. Could this be 0? Good question. Well, I hope now it works. Let's see. Lambda here, 1 here, 2 here, minus here, plus here. Is that right? Yeah, works out. Lambda is -1 and 2. So there are two solutions in my fundamental system. One solution is based on e to -t, and such solutions go towards the center, towards the origin. That's the good news. Then there are some solutions that are based on e to 2t, and they go away. So it's a mixed situation. Some solutions are going towards my stationary solution, and some are going away. That's exactly saddle. Let me put it here. Or one can simply remember the chart which I've been drawing here. If you remember, there was a chart, 6 situations, and each of them has a description given in terms of eigenvalues. So if the eigenvalue is complex with positive real part, you get unstable focus. If you have real eigenvalues which have distinct signs, you get a saddle. Wonderful. So as you can see, it really does work nicely also for nonlinear systems. This linearization is the key. You can also use it to approximate solutions when they are near this center. And it needs to be a stationary point, need not be. Okay? So if you just have some point that is really of interest to you, and you want to know what's happening around, you use it in this Taylor expansion, and you approximate your system by a different formula, but then you have to do some more work. It's not enough to just look at the matrix. But this is a very fruitful idea, linearization, very extremely strong, I would say. Very good tool. Let's go back to this example. You may say, okay, wait a second. Okay, we didn't really see any linearization in action, did we? I mean, I took the point 1, 1, I found the Jacobi matrix, and then I just jumped right into the conclusion. So what can we say about this linearization? Let's have a look at it. Our function f, the right-hand side, gets replaced by the following thing. And I look at the formula over here. I take my Jacobi matrix with the center substituted into it. So it will be the matrix O, 2, negative 1, 1. And this one multiplies the unknown vector, xy. Then there is minus this matrix multiplying the center, which is my stationary point, 1, 1. How much is it? Well, let's see. Over here, I'm getting 2y. I'm getting minus x plus y. And I'm subtracting 2, 0. So this is really 2y minus 2 and y minus x. What does it mean? Well, it means that this system that I have over here gets replaced by another system of differential equations that have this as the right-hand side. Do I have some room over here? Yeah. Let's put it here. So for 1, 1, the linearization works like that. X dot is 2y minus 2, and y dot is y minus x. Now, I commented earlier that the second equation is linear, so the linearization just kept it. It just changed the first equation. Now, we have a new system, old system, new system. They are not the same, definitely not. But 1, 1 is a stationary point for both of them. And I hope that nearby this point, the solutions behave the same. And I can actually check, because I can find solutions here, I can find solutions here, or rather orbits. Again, I use the vector field for it, and I can compare. This will be interesting. Let's have a look at it. So here is my code. What you can see in this picture, perhaps I can enlarge it still a little bit more. The blue arrows, that's the slope field for orbits on the neighborhood of 1, 1 for the original system. So this is blue. And this linearization, based on this formula, based on this approximation, is in red. And you can see that when you stay near the point 1, 1, which is the center of our attention, then the red and blue arrows, they agree essentially, they match. But when you go away, they start being different. And like over here, they are leading in totally different directions. They're almost perpendicular. So that's to be expected, because linearization is local. But you can notice that when you are nearby the point 1, 1, then there is a perfect match. So really, this linearization does provide good information, relevant information about the original system, as long as you stay close to 1, 1. Okay, just for the sake of completeness, let's have a look at the point negative 1, negative 1. So the right-hand side now gets approximated by the matrices 0, negative 2, negative 1, 1. I'm multiplying by the vector xy. So we are here. And now I'm subtracting our matrix. Zero, negative 2, negative 1, 1. Multiplying our center of attention, which is negative 1, negative 1. How much is it? Well. Here I am getting negative 2y minus x plus y. I'm subtracting the vector, which is 2 and 0. So this is negative 2y minus 2, y minus x. So when we stay close to negative 1, the original system gets replaced by a new system which looks like this. X derivative is negative 2y minus 2, and y derivative is y minus x. I can see it from there. And again, let's compare the two systems. Here we have another picture. Again, the blue arrows, that's the original system. And we see orbits, not the solutions. Let's be careful. These are the trajectories of the solutions. And the red arrows, that's the linearization. And just as before, when we go away from this point, -1, then the red and blue arrows, they start getting different. This is to be expected, but if we stay close, they match perfectly. They are exactly the same arrows. So this system and the original system, they behave exactly the same when we are nearby, -1, and it all makes sense, okay? And that's the main message of this linearization business. So we can do classification, even for general systems. Let's have a look at them. But before we leave, one more picture. This is the slope field for orbits for the original system, and I just put some numerically calculated orbits so that you can see what's happening. On the right, there is this unstable focus, the outgoing spirals, and we see some solutions. Some of them are going around almost all the way, and some of them are going around just a little bit, and then they leave, they go away. And on the left, -1, there is the saddle, and the solutions are going from the lower left corner, and they are sort of splitting. They are going around this saddle. They don't want to go there. Okay? So that's a very nice picture. As I said, this is a system of differential equation that looks deceivingly simple. It looks very nice, but it's complicated. It cannot be solved analytically. The shape of orbits cannot be determined analytically. And as you can see from the solutions, there are all kinds of different behaviors. This is really nice, really interesting. So even a very simple system of differential equations can actually, let's say, carry in it all kinds of different behaviors. This is really a very nice system. And that's the happy end. There's essentially nothing more to add. This linearization, a perfect tool, it allows us to classify even nonlinear systems. Of course, this all works very well also for, let's say, systems of higher dimension. Because if you have more equations, like 3x3 system, 4x4 system, you simply find the Jacobian matrix, you find lambdas, and you look at them. What signs do they have? Do they have imaginary parts or not? And essentially, these pictures can be also imagined in 3D, in 4D, and so on. Like in 3D, the solutions are cycling around your stationary point, or perhaps they are going inside along some curves, or perhaps going outside. So all these 6 situations, they make perfect sense also in more dimensions. So this classification is done not just for 2x2 systems, but also for higher dimension systems. And that's it. Now, if you are curious, I'm going to do a bonus. I'm going to do a thorough investigation of 2 systems that I can solve, actually. So these will be linear systems. And we will see how those theoretical, let's say, musings and those theoretical expectations actually reflect in an actual situation. So this is not really all that necessary, but I think it's a nice accompanying story which shows how these things really work. Here is our first example. A 2x2 system, is it linear? Oh yes. 2 linear combinations on the right. It's not homogeneous because there are some extra right-hand sides, but they do not feature t. They are just constant, so there is a chance for finding a stationary solution. Let's have a look. I take the right-hand sides and make them equal to 0. I'm finding stationary solutions. Well, -2y plus 2 is hopefully 0, and 3x minus 7y plus 4 is also hopefully 0. Let's see, from the first equation, y should be 1, definitely, no other way. I put it into the second equation, minus 3 divide x is 1. So I can say that 1, 1 is an equilibrium or stationary point. Or if I want, I can talk about solutions. I can say that y, s, t is equal to 1, 1. That's a stationary solution. Or perhaps you may want to say that x as t and y as t is 1. That's a stationary solution. And of course, I should put the region of validity always. And also here, a small one. Okay. What do we know about this equilibrium? Well, first of all, we can sketch it. 4 stands over here. Well, how much room will I need? Let's be generous. X and y, here is 1 and 1. Okay, that's our stationary solution, or equilibrium, or stationary point. Now, classification. Classification needs to know the matrix of the system. What is the matrix of the system? It's actually 0, -2, 3, -7. Now we find the determinant of minus lambda, -2, 3, -7 minus lambda, which is essentially lambda squared, plus 7 lambda, that's a lot of lambdas, plus 6, and this is perhaps 0. Well, let's see, are we lucky? Lambda, lambda, plus, yeah, plus 2, plus 1, plus 6. It was either 1, 6 or 2, 3, or perhaps we go to the discriminant formula. 1, 6 does work. 1 times 6 is 6, 1 plus 6 is 7. Yeah? Our lambdas are -1 and -6. So let's make some conclusions. We can say, based on our previous theorem, that 1, 1 is a stable stationary solution. How do we know? Because the lambdas are negative. We had a theorem about it. You just look at lambdas and the signs they decide, signs of the real part. But in this case, these are real eigenvalues, so no problem there. Classification. If you remember the chart that I draw, negative lambdas, that's the upper left corner, stable node or stable node. But you can sort of visualize it. When you have these lambdas, in the solution you will have two exponentials, e to -t, e to -6t. They both go to 0. So the solutions will be going towards the origin, and then we shift it to 1, 1. So this is stable knot or node. You can choose whatever you want. Okay, so the classification is done. But you say, oh, wait a second. Didn't we ask for more? Didn't I promise more? Well, yeah, let's investigate. We know that the solutions actually go to the stationary point 1, 1. They should go there. But how? That's an interesting question. So let's ask about a general solution. Well, general solution consists of two components, a particle solution and the general homogeneous part. Particle solution, where do we get it? Well, we already have it. This is a stationary solution, and therefore it is a solution. We can use it as YP. Wonderful. Now we just need to figure out the solution of the associated homogeneous system. So we go to lambdas, we find eigenvectors, we put it together. No big problem, no big deal, in fact. So when lambda is -1, then I put -1 for lambda here, it becomes 1, -2, 3, -6. Now the second row is triple of the first one, which is okay, that's how it's supposed to be. It's supposed to be singular, so probably I did make a mistake so far. This means that the equation is v1 minus 2v2 is 0, and therefore I can find eigenvector. I put 1 for v2, and then v1 will be 2. So I have lambda, I have eigenvector, and I can use it to create the first vector in my solution, or rather in my fundamental system. It's e to -t, because lambda is -1, and the eigenvector. And this is taken a times. And then b times the second component in my fundamental system. So let's see. When lambda is -6, that's a big number. Usually at school you don't get such huge eigenvalues. You get like 1 or 2 or 3 at most. Okay. Let me write it properly. So it's negative 6. I'm putting a negative 6 here. I get 6, negative 2, 3, negative 6, negative 1. And now the first row is double of the second row. So again, it's a single matrix. And I use the second row for my equation. 3v1 minus v2 is 0. Let's see, I will put 1 for v1. And I get 3. When I have a new chalk, I get 3 for v2. Okay, here's my lambda. Here is my v. 1, 3, e2 negative 6t. T, let's say, greater than or equal to 0. I don't really care much. Okay, I look at it and I say, okay, that's my general solution. What happens when I send time to infinity? Well, then in the solution, exponentials go to 0, and this whole vector tends to 1, 1. Well, this just confirms that my stationary solution is actually stable. So, no big surprise. Now the good question. How does it go there? How does this y go to 1, 1? Let me focus on the homogeneous part. In the homogeneous part, we can see two components. And we know that when two exponentials meet in a linear combination, then the one with larger exponent is dominant. So I'm going to factor it out. I'm going to factor out e to negative t, and I get a times 2, 1, plus b times 1, 3, e to negative 5t. Now what happens when time goes to infinity? Well, this part goes to 0. And therefore, this whole bracket starts looking like a times 2, 1. If a is not 0, one should be careful. And of course, this part goes to 0, but this is not surprising. We are interested in direction. So let's split two cases. Case number 1. What if a is 0? Well, if a is 0, then my homogeneous solution is just a multiple of the vector 1, 3 multiplied by the exponential e to negative 6t. Because I can go back to this formula. This becomes 0. I'm just looking at this. So my solution is scrolling towards the origin. And when I put it here, it's scrolling towards 1, 1 from the direction 1, 3. That's interesting. Direction 1, 3. How does it look like? We put one part here and 3 parts here. It's a fairly steep, I guess, 1, 2, 3, I guess like that. That could be the direction 1, 3. And that's the direction of the orbits for this particular type of a solution. So if you start somewhere on this line, and it doesn't really matter where, the solution will be going along this ray towards the stationary point 1, 1. Which brings us to an interesting question. What happens if b is 0? If b is 0, then these are just multiples of the vector 2, 1. Vector 2, 1, how does it look like? It looks like this. 2 and 1. It's this direction. So these are the two basic directions that lead towards our stationary point. This is direction 1, 3, and this is direction 2, 1. And let's make a note that this one works with B, and this one works with A. What happens if you have a vector which has both components, which means that's the case too when A is not 0? Then, when t is really, really large, then in this bracket, the second part can be ignored, and the solution is approximated just by the first part. So it will be a to 1 e to negative t. So if you start at some other place, here, 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 then the solution at the start can go in all kinds of ways. But eventually, as we approach this stationary point, we should be approaching it from direction 2, 1. So I expect something like that, and something like that, something like that, something like that. So this direction to 1, it's privileged. If you want, you can figure out the formula for this line, and you can easily figure out which one it is because it's given by a vector formula over here, or it's given by a parametric formula if you want to parameterize it. No big deal. This one is actually given as y minus 1 is 1/2 x minus 1. That's this line. And this line is y minus 1 is 3 times x minus 1. Okay, so this is just ordinary analytic geometry, no big deal. But this is an interesting picture. We know that it's stable knot, but we actually see that there is more to it. There is one privileged direction which is attracting all the orbits, with exception of those orbits that start on this other direction. So this poor guy, 1/3, if you start there, you stay with it. But if you start even a little bit away, this guy overwhelms the direction. This guy overwhelms the tendency. Even if you start just like here, you will go this way. Is that true? Well, let's have a look at it. I have a maple code, and I have some vector fields for you. Let's see. The green curves, the green lines, that's exactly the 2 basic directions, and that's actually solutions. I asked directly for solution which starts at this place, and I asked for a solution which starts at this location, this location, this location. So I didn't cheat. I didn't ask computer to draw 2 straight lines. I asked, please plot 4 solutions that start here, 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 and I use green for it. And the computer found the solutions, and they are really straight lines. And then I put some other starting locations, and that's the blue curves. And as you can see, they are really curving so that they are hugging this line which is more flat, the dominant direction to 1. So our theoretical analysis is matched by the actual outcome, which is interesting. This was a typical example. What I mean by this, the combination of eigenvalues allowed us to hit one of those 6 situations. Let me show them again. Okay. So that's the 6 situations, and our example was representative of the upper left one. But I commented that these are not the only possibilities. There are also some, let's say, rare cases when things are still different. So the last example for today's lecture will be, again, a system of linear differential equations, but a non-traditional one. Let's see. Our last example is again a system which is 2 by 2. It's linear, and this time it's homogeneous. And because it's homogeneous, there is definitely a stationary solution, 0, 0. But let's do it properly. We take the right-hand sides, we make them equal to 0. X minus 3y is 0. X minus 3y is 0. Well, actually that's a singular system. There is just one solution, which is y is equal to 1/3 x. It's one solution, but in 2D. It's a line of stationary points. So stationary points, in fact, look like this: x, 1/3 x, where x can be anything, any real number. There is infinitely many stationary points. Now let's put them on the board. Here is the trivial stationary solution, and all of them are along this line, y is equal to 1/3 x. These are all stationary points. Interesting. Now, because the system is singular, also the matrix of the system is singular, it means that one of the lambdas must be 0. And therefore, the trivial stationary point is unstable. And we know that because lambda is equal to 0 is not less than 0. That's the argument. Okay, let's see. Our matrix A is 1, -3, 1, -3. We find the determinant of 1 minus lambda, -3, 1, -3 minus lambda, which is, let's see, lambda squared Well, 3 lambda minus lambda is plus 2 lambda. Minus 3 plus 3. This is lambda square plus 2 lambda. And perhaps this could be 0. And the answer is yes, it's 0 if lambda is 0 or negative 2. So there is one direction where the solutions are not approaching the origin or going away. It's a stationary type of a solution, e to 0 times t. And then the second component in the fundamental system has e to negative 2t. Before we write the general solution, we should look at eigenvectors. Let's see, when lambda is 0, then the matrix we are looking at is, well, exactly this one. I use the first row to create my equation. v1 minus 3v2 is 0. So the eigenvector could be, well, let's see, I put 1 for v2 and 3 for v1. That's for lambda equal to 0. So my general solution is a times 3,1 times e to 0, which is 1. So I can leave it like that. Interesting. What is the vector 3,1? Well, that's exactly the vector which is giving our line. Well, perhaps this is not exactly 3 to 1, but it's supposed to be the one. So depending on what a I put in here, all these solutions are just dots. They are stationary solutions. So I get them not just by looking for stationary solutions, as I did at the start. I obtained them from solving this system, but I can also see them here in my formula for the solution. Then there is another component, and that's where things get interesting. Let's see, when lambda is negative 2, then we get the matrix 3, negative 3, 1, negative 1. Is it singular? Yes. So things are okay. I use the second row for my equation. v1 minus v2 is 0, and the vector is 1, 1. This is actually fairly routine. So my second solution has direction 1, 1, and exponential based on a negative 2. And of course, this part goes to 0. So all my solutions look like this. First of all, I fix some stationary solution, and then to this I'm adding another vector which is going in direction 1, 1, or perhaps negative 1, 1, depending on the sign of b, and it's multiplied by some number which is decreasing in size. So I choose my stationary solution, for instance, this one, and then I'm adding some component which is in the direction 1, 1. Direction 1, 1, that's the diagonal, which is about this. And this component is getting smaller and smaller and smaller. So the orbit goes like this. And if I start here, the orbit goes like that. And if I start here, the orbit goes like that. So these are the orbits. They have direction 1, 1. So, oh, okay. I slipped out. This should be 1, 1, direction 1, 1, okay? But okay, this is just a sketch. On the other hand, if I start here, again, I'm going in the direction 1, 1, and I'm going this way. Direction is 1, 1. What does it mean? Well, imagine that we are sitting at the origin and we move away a little bit. If we move in this direction, we return back along our orbit. But if we move in this direction, then the orbit moves us here. We never get back. And that's why this guy is unstable. And the same argument applies to all those stationary solutions. If I start at this stationary solution and I displace my location, or let's say the bug is sitting here, and I displace the bug, then it will go in the direction 1, 1, which brings that bug to this location. Not here, but to a different place. So also this guy is unstable. All these stationary points are unstable. Now, this is a very strange picture for orbits, and we definitely do not see such a picture in our list. because as I said, these are typical situations, but there are also other possibilities. Fortunately, in applications, we generally do not get single matrices, so we do not have to worry very much about such strange situations, but they can appear. And we can see it for linear equations directly by analyzing our solution. And if our system is not linear, then perhaps we can use linearization. Okay, the last trick. Here is Maple, and I will ask it again for some solutions. And you can see them here. The green curve, that's the solutions that are stationary. It's actually infinitely many stationary solutions, their orbits, because these solutions are stationary, and therefore their orbits are just dots. And then there are those blue curves. I started at different locations, and I was moving towards this green line in the diagonal direction, essentially. And you can see the arrows. They're all going in the diagonal direction towards the green line. So this is a new situation. It wasn't on our list, but because it's rare, we don't really care. And that's it. So this much for analyzing solutions of systems. And in the next lecture, we will ask how to get those numerical solutions, which I have been actually showing several times. So a good question is, where did I get them? Where Maple got them? See you there. It's possible, but for that, we actually need a slightly different point of view at the solutions. We saw the solutions as individual functions. That was nice. We saw them as two-dimensional, whatever dimensional curves. That was also nice. But now the time comes to try yet another point of view. That was nice. That was efficient, and I like it. OK. Here we go.